got in the way of problems with vectors?
So the first one says show that the directed line segments of RS and OP are equivalent. And R equals -4 and 7. S equals -1, 5. O equals 0, 0. And P equals 3, -2.
Okay. Here's the thing about vectors. That vector is identical to that vector, which is identical to that vector, which ultimately is identical to a vector that starts at the origin. The only thing that it takes to make vectors equal is the same magnitude and the same direction. That's the difference between vectors and scalars. If you take 5 seconds to do something, then it's a scalar amount, 5. But a vector has 2 different things associated with it. It's got magnitude and it's got direction. And that's all that it's got. In other words, if that magnitude is 5 and its direction is 40 degrees, and each one of these other vectors also has a magnitude of 5 and a direction of 40 degrees, they're the same vector.
Okay.
So, if we go back to our problem, I'm trying to figure out how to explain this. Let's look at vector OP. Vector OP goes from 0, 0 to 3 minus 2. So that's that vector. And what they want is, let's draw R and S. R is -4, 7. Put it right there. And S is -1, 5. So there's our S. Well, certainly the way I've drawn it, they look similar, but do they have exactly the same angle? Well, what tells me that? What about these 2 vectors do I need to know?
Slope?
Yeah. What's the slope of RS?
Would be -3
Well, that's 5 minus 7.
Oh, right, okay, so -2 over 3.
Huh? So -2/3 is the slope of that. What's the slope of vector OP?
-2/3.
Okay, so that tells me that they have the same direction. They both have the direction of whatever that angle is.
Okay.
Now, do they have the same magnitude? Well, let's draw a little triangle here. What is the length of RS? Or the modulus, if you want to call it that.
Would that be 3?
Well, it's the hypotenuse of that triangle,
Oh, okay,
right?
yeah. So we would do, Sure.
Well, the hypotenuse of a triangle, and this is something you really want to memorize because you're going to have to do it so many times in the next couple of years. The hypotenuse of any right triangle is the square root of the sum of the other sides squared. And let me put a delta in there. Doesn't matter if it's negative or positive. What is the difference in the x-coordinates for RS?
3.
And the difference in the y-coordinates?
2.
So that's square root of 13 is its magnitude.
Okay.
What's the magnitude of OP? It's also the hypotenuse of that little triangle.
So it would just be 3 squared plus 2 squared?
Yeah, the square root of that. So it's also the square root of 13. Okay? So if they have the same magnitude and they have the same slope, they are the same vector. What's theta? Even though they didn't ask for that. This, if I'm looking at this triangle here, this dimension is 3, this dimension is 2. What is theta? Inverse tangent of what?
2 over 3?
Yeah. Or you could say 2 over, you could say minus 2 over 3 to make sure we end up with a negative angle. As long as you understand the picture and the diagram, then it doesn't really matter what the sign is. That angle is the inverse tangent of 2 over 3. If you want that angle relative to our unit circle, then it's the inverse tangent of minus 2 over 3, which gives you a negative angle. And that's what that really is a negative angle. Okay? But they didn't even ask for that angle, but they will. And when you're dealing with vectors, this angle is very important. And it's one of the few things where here's what the formula is. The angle is always the inverse tangent of y over x if x is greater than 0, but it's equal to the inverse tangent of y over x plus pi if x is less than 0. And there's a lot of different ways that they try to get you to memorize this. They don't all define it this way, but I've found that that's the best way to define theta. Okay, and this is also strange. In other words, you haven't dealt with this ever before, where we have to add pi not if y over x is negative, but if x is negative. Not the y over x, but just the x. And then that angle, you have to add a pi to it. It doesn't matter what y is. If x is negative, then you add pi to that angle. Well, in this case, x is positive. It's a positive 3. So I would use this. And if I use the negative 2 for y, then I get the inverse tangent of minus 2/3. That's going to be a negative angle. So it works for this. Now, what if I said to you, What's that equal to? In other words, this covers x being greater than 0 and x being less than 0. What if x is exactly equal to 0?
Then it doesn't work, then, right?
Actually does. This is the first time in your life you can divide by 0. And that's why I brought it up. It's because it's so strange. Theta is equal to pi over 2. When the inverse tangent of any number divided by 0 is going to be pi over 2, or minus pi over 2. Think about what the tangent curve looks like. Here's your tangent curve. At minus pi over 2 and at pi over 2. And there's the tangent curve. So the inverse tangent of infinity is pi over 2. And that's what that means, is that's infinity. And it's only infinity because you're dividing by 0. And it's the one time you can divide by 0 is when you're taking the inverse tangent of a number divided by 0. That's pi over 2. Okay? So that's the other thing about vectors, is knowing what that angle is. And the tricky part is it's only dependent on x, not y over x, and not even y. In other words, if I said theta was the inverse tan of, let's make y1, and let's make x1, well, that's the inverse tangent of 1, which is 45 degrees. But if I said theta was the inverse tan of 1 over negative 1, that's the inverse tangent of negative 1, which is negative 45 degrees. And I have to add pi to it because x is negative. So plus 180 degrees, I end up with a 135 degree angle. And if you think about the unit circle, that is where the tangent of 135 degrees is negative 1. And in other words, it would be the vector like that. Notice that that's negative 1. That's positive 1, y is positive 1, x is negative 1. Only if I add pi can I turn that from minus 45 degrees into the proper 135 degree angle. All right, what else do you have? I may be talking about stuff that you haven't covered yet, but
the next one. It's the same process, it's just different numbers.
well, let's just talk about that for a second. Anytime you have a vector where one of them does not have its endpoint at 0, 0, you can always turn it into a vector that starts at the origin. In other words, it doesn't matter what vector I have. I can have a vector that's way up here. I can always turn that in to that vector where one end is at the origin, and the advantage of that is that this vector requires me to describe two coordinates, two sets of coordinates. This vector is the composite vector where one end always starts at 0, 0. And the only thing I need to describe that vector is the coordinates of the ending point. So any vector between any 2 points can always be turned into a vector starting at the origin going to some ending point, like they did on this first problem. They took this vector that was between those two sets of coordinates and they turned it into this vector where 1 was 0, 0. Okay. Want to do that second problem? Or?
Yeah.
Okay.
Okay, so R equals 2, 1. S equals 0, -1. O equals 1, 4. And E equals -1, 2.
Okay. So for these two vectors to be the same, they have to have the same slope and the same magnitude. So let's figure out the slope of this one.
Okay. So that'll be -2 over, would that just be -2 over -2, so 1?
Correct? What's its magnitude? Remember, the magnitude's always going to be the square root of the sum of the difference squared.
Okay.
So it's going to be the square root of delta x squared plus delta y squared.
Okay.
What's
So
delta? What are each of those?
2 squared plus 2 squared.
Equals square root of 8. Now let's look at OP. What's the slope of OP?
That would be -2 over.
You can do these in either order, incidentally.
Okay.
When we were doing RS, it actually makes sense to do 1 minus minus 1 divided by 2 minus 0, only because it leaves everything positive. In other words, slope is, it's not just, it's not just y sub 2 minus y sub 1 over x sub 2 minus x sub 1. It can also be y sub 1 minus y sub 2 over x sub 1 minus x sub 2. In other words, you can go in whatever order you want. It doesn't change it as long as you're consistent. So up here, it actually makes sense to go 2 over 2. And this one, it makes sense to go that same way, 2 over 2, as opposed to -2 over -2. You know what I'm saying?
Yeah.
Okay. So just as long as you remember that whichever way you go, you have to go the same way for both the x and the y coordinate. But either way you go, you get 1. And then what do you get for the magnitude of OP?
Square root of 2 squared plus 2 squared.
Yep, square root of 8. And even though that's not simplified, probably in this case we don't need to, since their directions were just prove that it's the same vector. Or how did they put it? Is that what do they use the word same? Prove that RS is the same as OP?
Prove that they're equivalent.
They're equivalent, okay. They're equivalent. That's probably a better term. Because clearly they're not exactly the same, but they're equivalent. That's a better way to put it. Okay. This one's a little different in that neither vector started at 0, 0. But we could certainly make a vector that started at 0, 0 if I wanted. It's going to have a slope of 1. It's going to have a magnitude of square root of 8, which means that side is 2 and that side is 2. So there is a vector that is equivalent to both RS and OP. The only difference is that this vector starts at the origin, which means I could define it with only one set of coordinates, 2, 2. And that's valuable in a lot of situations. In other words, we take a lot of vectors and we automatically turn them into vectors that start at the origin. Because then you're always looking at this picture and there's theta, and so forth and so on. All right, what else? Well, you're going to get into some hard vector problems too, only because you're taking an honors course. And vector problems can get very hard. So maybe not for this week, but for next week, you might even want to send me a copy of some of the problems in advance, because by next week you're going to be on the hard vector problems. And those can be tricky, very tricky, depending on how hard you get. I mean, you can be taking vector algebra in third year of college. It gets that hard. I just don't know how hard you're going to have it. At this point, it's still pretty basic. But so do you have any problems different than those two?
Yeah. So these ones, the next couple, it gives several points that are going to remain the same, and then it wants to find component form and magnitude of the vector.
Okay. When they tell you component form, that means the vector that starts at 0, 0.
Okay.
I found component form of that vector right there. The component form would be 2, 2, as long as you're starting at 0, 0. So taking these vectors and reducing them to component form is an exercise that you have to do quite frequently. All right, so what's the vector?
So it says P equals -2, 2. Q equals 3, 4.
Okay.
R equals -2, 5. And S equals 2, -8. And the first one is vector PQ.
Okay. What's the component form of this vector? And the easy way to do this is to make P be 0, 0. What would I have to do to Q?
Add 2 to X.
There you go.
Y.
There's the component form. Now, let's check our slopes and magnitudes. First of all, what's the magnitude of PQ? Square root of what?
Is that going to be 5 squared plus 2 squared? Or
Yeah, it's the square root of delta x squared plus delta y squared. So it's 5 squared plus 2 squared. Well, that's the same magnitude as our component vector, because our component vector starts from 0, 0.
Okay.
So its x is 5, its y is 2, its magnitude is the square root of 5 squared plus 2 squared. What's the slope of the component? 2/5. What's the slope of PQ? 2/5.
Okay.
So they have the same slope, they have the same magnitude, they're equivalent vectors. But you'll notice that the easy way to turn it into a component vector is just to take one of the points and do whatever you have to do to make it 0. I had to add 2 to the x and I had to subtract 2 from the y. So what's the component for RS?
So that would be 4 and -3.
No, what do I need to do to the y to get it to be 0? I got to subtract 5.
Okay, so negative. Okay.
Okay. What's the magnitude of RS?
That'll be the square root of 4 squared plus 13 squared.
Yeah, and we don't care whether that's negative or positive because we're squaring it.
Yeah.
So all we really need is the distance between these points. It's 4 units from 2 to -2. It's 13 units from -8 to 5. Whether you go from 5 to -8 or -8 to 5, it's 13 units. Okay? Magnitude of the component, same thing. Square root of 4 squared plus 13 squared. Slope of the component is rise over run. Well, that's the same as the slope of RS. Minus 13 over 4. Did we answer everything that we're looking for?
Yeah.
Okay.
The next one, they use the same values at 2QS.
I'm sorry, they use the same value as what?
They use the same values that we just used for those two.
Okay.
And they're using 2QS.
Say again, I'm not quite getting what you're saying.
So P is still going to be -2, 2.
Okay. Q is...
But it's using Q and S, and there's a 2 in front of it.
So Q is equal to what?
Well, Q is going to stay the same, like those values are the same, but it's, okay, so it's written as 2 vector QS.
Okay. I think I get now what you're talking about. So they're asking what is 2 QS or QP? In other words, we have the same 2 points, R and S?
It's for Q and S, not QP.
Right. What was the points on R and S again?
S was...
I guess that's the only one we need. Yeah.
2, -8.
So they want the vector QS, and they want it in component form, and they want the magnitude of it? Right?
Yeah.
Okay. What's its component form?
Well, do we need to worry about that 2 for now? Like, what do we do?
Oh, they want 2 times QS.
Yeah.
That's just a scalar multiplier. So whatever the magnitude of QS is, we're going to multiply it by 2.
Okay.
Okay? So let's start by what's the magnitude of QS? Is this what your class uses, these absolute value signs for that?
Yeah.
Okay. And they call it magnitude?
Uh-huh.
Okay. It's also called modulus. If you might hear that word sometimes also. So what's the magnitude of QS?
So that'll be 1, or square root of 1 squared, just 1. Okay.
Right? In other words, the square root of 1 squared plus 12 squared, which is
144.
Right. 12 squared is 144 plus 1 is 145.
Oh, right.
Now, that does simplify a little bit, I think. No, maybe it doesn't. No, I don't think that does simplify. That's not divisible by any of your perfect square numbers. Not divisible by 4, not divisible by 9, not divisible by 16, or 25, or 36, or 49. That's simplified as much as I can simplify it. So, 2QS is 2 root 145. Is that all they wanted, was just the magnitude?
The component as well.
Okay. What's the component for QS?
For QS is
And you use these inequality signs to
yeah.
Okay, go ahead.
What do we do? 2 minus 3?
Uh-huh.
Okay, so -1 and -12.
Exactly. Notice that it has the same modulus as QS does, square root of 145, or the same magnitude rather. Also has the same slope. It's 12 over 1. Now, this is not 2QS, that's QS. If I'm drawing QS, and this is QS, not that it is, I haven't bothered to check my points here, but if that's QS, then this is twice QS.
Okay.
Just twice as long. That's what the magnitude means. And when you start applying vectors to things like, the key things that vectors is really used for are an airplane flying. It's flying with a certain magnitude. Its magnitude is its velocity, and its angle is its direction. Okay, so if I said an airplane was going at 500 miles per hour, that's 500 miles, and it's going at an angle of 30 degrees from due east. And now I have a wind that's going 50 miles an hour, due west. Which way does the airplane actually go? Well, the way you solve these problems is you break each of these into their component vectors, and then you add the x component and the y component, and whatever you end up with is the resultant vector. When you add this 500 mile per hour vector to this 50 mile per hour vector, you can get a resultant vector. I'm sure that you've been through the adding vectors and subtracting vectors and that.
Yeah.
That's always where they start, with vectors. And that's easy enough to do. But the truly difficult problems with vectors is when you're dealing with direction and speed or force and direction. For example, the force ones might be this. This is always a good problem. There's a soccer ball or a rugby ball, and you got 3 people tugging on it. One's tugging in that direction at 100 pounds. Another's tugging in that direction with 50 pounds of pressure. And a third one is tugging in this direction with 70 pounds of pressure. And the ball isn't moving. Well, no, excuse me, I gave you everything. And there's a third person tugging in this direction with X amount of pressure. And the ball is not moving. Can you solve for X? And the answer is yes, you can. The fact that the ball is not moving means that the net X force is 0 and the net Y force is 0. So by breaking that into its components and that into its components, and if you know the direction of that, then you can solve for X, because you know that all of the net X has to add to 0 and the net Y has to add to 0. So that's why we break vectors into their components, is because when you have a combination of vectors, you can figure out the resultant that way. I mean, this is a particularly clever problem because the ball is not moving, so you know the net X force has to be 0 and the net Y force has to be 0. If it wasn't, the ball would be moving. In other words, if this guy starts tugging with 120 pounds, that's adding force in that direction, that ball is going to move. If it wasn't moving when he was only tugging with 100 and now he tugs with 120, that ball is going to move. So we would be able to figure out a net vector as to what would happen to that ball.
Okay.
And it applies to force. Let's say you have a sign hanging from a building. And you want to put a brace there. Well, if this sign weighs 100 pounds, you need to determine the force vectors on this metal bracket, and this metal bracket in order to build your sign. And you do that using vectors. And why? Is because force is a vector. This is a 100-pound force with a direction towards the center of the earth. That is that vector of that sign. And so you have to make sure that the combination of those 3 braces supports a 100-pound force going down. We won't get into that tonight, but that's where you're headed. By next week, you're probably going to be giving me problems like that. And when you get to that point, that's where I would say, please send them to me in advance so I can take a little bit of a early look at them.
Okay. Should I just email the...
Yeah, you can just take if it's out of your book or out of some review material, just take a picture of it and send it to my email sometime before our session. Preferably like at least a half hour before our session. That way it gives me a little bit of time to look at it.
Okay.
All right. Yeah, vectors. Vectors are you taking physics this year?
I took last year.
Okay. Well, you ran into vectors with physics, I'm sure.
Yeah.
And it was probably confusing because you hadn't had it in math by then, huh?
No.
Yeah. Yeah, you got to get these all in the right order. You probably need to take precalculus before you take physics, or at least at the same time, but not in the reverse order. Because you haven't had vectors at all in any kind of math before now, have you? Did you get vectors at all in Algebra 2?
No, I don't think we did.
No, I don't recall any of my Algebra 2 students having vectors either. That's usually you don't get it until pre-cal. Okay, what else you got?
Okay, so it says to find the complete form of the vector. Okay, so u equals -1, 3. V equals 2, 4. And W equals 2, -5.
Okay.
And this first one there is U plus V.
Okay, that's very straightforward. Just add the individual components. So U plus V would be what?
Would be 1, 7.
Okay. In other words, addition, subtraction, multiplication is always very straightforward.
Yeah. I don't think we really need to do that section here.
Okay. Finding the component is also very straightforward. Now, I do have a, what was U again? U is what?
U was -1, 3.
Now, if I said the component of UV, I don't even know how you would write that. I guess you would write it like this. I'm not sure whether U needs to go to 0, 0, or V, or either one. I'm going to say the first letter needs to go to 0, 0. So the component would always give us the vector where U would be at 0, 0, and meaning I got to add 1 to this and subtract 3 from this. So there's the component of UV. I could also make V 0, 0 going to U, but then it's going in the opposite direction. And those are not equal vectors. In other words, if I have a vector like this, that's not the same vector as that vector there. They're going in different directions. Their angle would be 180 degrees opposite. So how we define the component really does matter. We do need to let U go to 0, 0 if we're going to call the component UV. If we wanted to call the component VU, then I would force the V, X, and Y to go to 0 and alter the U. Okay, what else about this question? Maybe. That's the only thing I can think of that might not be completely clear when you're doing these components, is which one you force to the 0, 0.
Yeah, this part's also pretty straightforward.
VW is an interesting vector. Let's look at VW before we go on, because this is going to illustrate what I was talking about before. So what's the component of VW, first of all?
So that'll be 4, or no, 0.
Yep.
And -9.
What's the slope of that vector?
Is that going to be -9 over 0?
Right.
So,
And that is a legitimate slope. That's a vertical line. Notice where these 2 points are. If I graph them, they're both at 2, one is way up here, the other is way down there, that's a vertical line. So it's going to have an undefined slope, or an infinite slope. I don't really like the word undefined. At some point in math, you start using the word either infinity, or I like infinity better than undefined, because it's really infinite. In other words, this slope is an infinitely steep slope, because we're dividing by 0. And notice that that vector, if I were to draw the component, it goes from here down to there, right?
Yeah.
So theta, in other words, the angle that this vector would measure from the x-axis should be 270 degrees, right?
Yeah.
Okay, well, let's figure out what it is. I said theta is the inverse tangent of y over x, or the inverse tangent of y over x plus pi, depending on whether x is positive or not. In this case, x is 0. It's neither positive nor negative. So when you take the inverse tangent of infinity, you get pi over 2 plus pi is 3 pi over 2, and that's what that angle is. I could also take the inverse tangent and get minus pi over 2, and that's also that angle. You probably haven't been taught this part yet. The only reason I bring it up, you might not even get taught that until you get into polar. And polar is coming right after vectors. But I think you get it with vectors also, because you get a lot of problems with vectors where you have to figure out that angle. And you have to make sure you're in the right quadrant. Otherwise, you'll, get the answer to whatever problem you're working on wrong. But when they write the component vectors, is this the terminology they use, or do they use something different? Or do they just call it UV with an arrow over the top like that? I think you can.
It's an arrow with just the top point for it, like they don't have the bottom past the arrow.
Oh, down here they don't. In other words, they would just call this VW like that?
No, it's like if you drew the arrow, but you didn't the third line into it. You just did the first 2 lines of an arrow. If that makes any sense.
Well, let me draw a few. I'm not sure what you're saying. Are you talking about that?
Yeah.
Really? Wow. Okay.
Like that.
So that's just for all vectors. That's just their vector terminology there? Or is that specifically for the component?
I think the component one, they might just call it U.
Well, notice the difference here. You defined U as a set of xy coordinates. So U by itself is not a vector, nor is V. That's just a set of points also. So if I'm going to talk about the line between U and V with a direction, then I need this terminology, and I need this over here. And this assumes it's the composite, because we define the vector with only 2 numbers. We don't define it as, the difference between the V's and the difference between the U's. All right. What else?
I don't think they have like a specific thing here for components then, like no specific symbol.
Okay. It's probably just this, the way I've drawn it there. In other words, you just talk about, you don't define vector UV in any way other than its components.
Okay.
You wouldn't define vector UV as being any way other than this. I mean, you could define vector UV as being the line between those two coordinates, but if you're going to define it as a vector, you assume that it's in component form when you write it like this. That means component form, meaning that the U side starts at 0, 0, and the V starts at 0, 0.
Yeah, the rest of this looks pretty straightforward.
Okay. Yeah, I'm almost certain the next thing you're going to get is an airplane problem.
Okay. Yeah, I'm not seeing any here, but I am familiar with those from physics.
And you got some wind direction. In other words, when you get in the airplane, you set its direction and you set its speed. But depending on what the wind is doing, you don't necessarily go in this direction or go at that speed. If the wind is working against you, like I've drawn here, then clearly that airplane is not going to go at 500 miles an hour. It's also not going to go at that angle that it's pointed. It's going to go a little bit north of that because the wind's going to push on it. So if you wanted to figure out exactly where the airplane goes, and you know that that wind is coming at a certain angle and a certain speed, you can figure out exactly what the resultant direction of the airplane and the magnitude is. And that's pretty much what every pilot does. You know, they can set their airplane to travel at 550 miles per hour and head 30 degrees north, but if they're into a stiff wind, they're not going to go 500 miles per hour. So if they want to know how long it takes to get from Denver to New York, they have to know all of these vectors. They have to calculate the wind vector and their settings, and then they can tell the passengers when they're going to arrive in New York. It's why it takes longer to fly east than it does to come back west. I don't know if you've ever flown to the East Coast, but that can be a 4-hour trip, and if you come back from the East Coast back to Denver, it can be a 3-hour trip. And that's because the prevailing winds are that way. So usually when you're traveling east, you're going against the wind. When you're traveling west, you're going with it. I might have that backwards, but the prevailing winds might go from west to east. I'm not 100% sure of that. But it shows you how important vectors are to virtually anything that can be described as a vector, which is forces, velocities. Can't think of anything else right off the top of my head, but those are the two primary things, are forces and velocities. Those have magnitude and they both have direction. All right, well, if you don't have any more problems, we can stop there.
Yeah, I'm done. Like, I have more problems, but I know how to do all of them. So
Okay. Okay. Well, okay, yeah. Like I said, if you're still on vectors next week and you're on the difficult problems, please send them in advance.
Okay.
Okay?
All right.
I'll talk to you next Tuesday.